Sound waves and its characteristics. Let us first draw the sound wave and understand what are all the characteristics and how we can represent it with the parameters with which we can measure the sound wave and we can describe the sound wave. So we will draw the sound wave with compressions and rarefactions. So this is a line of normal density. Remember, the sound wave is full of higher density and lower density with respect to the normal density. So we start with the line of normal density. And the wave with its crests and troughs, or we can call it as compressions and rarefactions. So the BF are the compressions which are having higher density and DH are rarefactions which are with the lower density. Now we will define various parameters from this graphical representation of the wave. The first parameter that we define is the wavelength. So the wavelength is basically a combined length of compression and an adjacent rarefaction. That means in this case, if we take the compression is ABC and adjacent rarefaction is CDE, so the wavelength is from A to E. This is the wavelength. Wavelength is represented by Greek letter lambda. So the other wavelength that we can think of is this compression and adjacent rarefaction, which is also a lambda. One more way of seeing wavelength in a longitudinal wave is the distance between the two consecutive compressions or the distance between the two consecutive rarefactions. That is, if we see the distance between B and F, B and F are the compressions, so this is also lambda, and in the similar manner between the consecutive rarefactions D and H is also lambda. So the distance between the two consecutive compressions or two consecutive rarefactions is also a wavelength. And another thing that we need to note down is a very important factor which we use in many problems is half wavelength. So the half wavelength is represented by lambda by 2, which is nothing but the distance between the center of a compression to the center of an adjacent rarefaction. So in this case, let us see, it is B is the center of compression and D is the center of rarefaction. So this is lambda by 2. In the same way, the center of rarefaction D to center of adjacent center, this is also lambda by 2. In a similar way, F to H. So the distance between the center of compression to a center of adjacent rarefaction is half wavelength, which is represented as lambda by 2. So the SI unit for this wavelength or half wavelength is meter. So let us first define wavelength. From this understanding, we know the wavelength. Combined length of compression and an adjacent rarefaction is called its wavelength. So lambda it is represented. So in this figure, these are the wavelengths. Now let's see another parameter which is called amplitude. What is amplitude? We know that the particles of the medium vibrate back and forth. So there is a displacement that is happening when they are moving back and forth. So what is that? So that is what we call it as amplitude. So the particles gets displaced temporarily from their original positions. when they vibrate, they get displaced temporarily. It's not a permanent. But the maximum displacement of the particles of the medium from their original position. Because before this vibration takes place, that is called its original undisturbed position. So from its original undisturbed position, the maximum displacement of the particles of the medium when a wave passes through the medium is called amplitude of the wave. Because when the wave is passing through the medium, these vibrations happen. And when vibrations happen, the particles displace temporarily. And that is when the compressions and rarefactions happen. So during that time, what is this displacement that the particles experience? The maximum displacement is called amplitude. So in the figure, if you see, the displacement is, if we have this, is denoted as PQ and R, and this is S, then the BP and FR, QD and SH, they are all the maximum displacements on either side of line of normal density. So this BP, for example, is amplitude. Let us define amplitude. So amplitude, the maximum displacement of the particles of the medium from their original undisturbed position when a wave passes through the medium is called amplitude of the wave. It is denoted by capital A. So the SI unit for amplitude is meters. SI unit for wavelength is also in meters. So let us write down the SI unit is meters, represented as small m, and SI unit for amplitude also meters, represented by small m. Basically, the amplitude of the wave is the amplitude of vibrating body which is producing the wave. So, what is producing the wave? Waves are produced by the vibrations. So, that vibrating body's amplitude. In this case, it's particles. Now, the next parameter is time period. So, this time period is nothing but the time that is required to produce one complete wave. So, one complete wave or one complete cycle. So, the way we have given in the figure, the one complete wave is A to E, A to C and C to E. So, A to E is one complete wave and E to I in the figure is the second wave. So, the time required to produce one complete wave, like in the figure A to E, is the time period. So, the time period T is defined as time required to produce one complete wave or a cycle. Is called time period of the wave. It is denoted by capital T. In other words, we can also say the time taken to complete one vibration. Basically, that vibration is what we are describing through these parameters. So, we will put all these definitions in terms of vibration too. Now, let's say, for example, from the graph, in the graph, we have from A to E, point A to E and E to I. This has completely two cycles. A to E is one cycle, E to I is one cycle. Let's say this A to I, it takes a time of 1 second. Then we say the time period T for one wave is half a second, because two waves it is taking 1 second. So for one wave it is 1/2 seconds or 0.5 seconds. So this is the time period for one wave. So that is the way we represent. Now SI unit for time period is seconds. Now let's see frequency. This is another parameter of the wave which is represented by f. What is frequency? The time period is time required to produce one complete wave. And the opposite of it is number of complete waves produced in 1 second. So the frequency is number of waves produced in 1 second. This is represented as small f, frequency. This number of waves is nothing but number of vibrations also. We can put it as number of vibrations per second is also called frequency. Frequency is represented as small f and SI unit for it is hertz. So it is also represented in terms of larger frequencies. We call it as kilohertz, which is 1000 hertz, and megahertz, which is 10 to the power 6 hertz. Because higher the frequency, we will represent it in a higher terminology. And what is 1 hertz? 1 hertz is 1 vibration per second, or we can call it as 1 cycle per second. This is frequency. And the last parameter, that is velocity or speed of the wave, which is represented as small v. So velocity or speed of the wave is nothing but distance travelled by the wave in 1 second is called velocity. And its SI units are meter per second or meter second minus 1.